Please, Leandro.
Yes?
Perfect, perfect.
Okay, thank you. So this presentation is divided as follows. First, a brief introduction. After that, the lattice discrete element method formulation. So I will going to present the model description, the results, and finally the conclusions. So axial compressor testing on concrete allows to measure the material compressive strain. Being this mechanical property fundamental to define its field of application. However, in this type of testing, many parameters can affect the compressive strain value, leading to an erroneous estimation. The experimental investigation of such an influence is expensive and time-consuming, and in such a context, numerical simulation can represent an alternative to integrate the experimental data. In the present work, so numerical simulations are performed by using a version of the lattice discrete element method, named LDIN, implemented on the Abacus software. The influence of the contact boundary condition between the sample and the testing machine, the slenderness levels, and the cross-section shape that is circular or square on the compressive strain are here numerically investigated. So the lattice discrete element method consists of a set of masses joined by bar elements characterized by a regular cubic arrangement. The bars are characterized by a bilinear constitutive law, which allows to take into account the irreversible effects of crack nucleation and propagation. Here in the figure below, it's possible to see the cubic arrangement used in the simulations and also the bilinear constitutive law applied to simulate the fracture in the lattice discrete element method formulation. A random field is introduced for the fracture energy, GF. So this parameter is modeled by a Weibull probability distribution, and it's assumed that the material fracture energy may be appropriately modeled as a random field characterized by a bilinear space correlation, defined by 3 correlation lengths in the coordinate directions. The proposed methodology can be used to represent so the heterogeneities of the material, like, for example, the aggregates in concrete. In the figure below, it's possible to see the bilinear constitutive law, the original bilinear constitutive law, the random field of the fracture energy, and associated with each bilinear constitutive law of different constitutive laws employed in the model. The LDIN is introduced in the Abacus explicit environment in order to create hybrid models between the lattice discrete element method and the finite element method, where it's possible to use each model's advantages and the potential. More details about this combination is available in the work of Schumacher. So, about the model description. 2 models are used to simulate the decompression test. Model A, where just discrete elements are used, and Model B, where a hybrid model is used with the concrete simulate with discrete elements, and the steel plates simulate using finite elements. 2 boundary conditions are used for each model, frictionless and fixed. Here in the figures, we have an example of the model A, where such a boundary conditions are applied directly to the nodes of the discrete elements. And here an example of the model B, where the boundary conditions are applied in the interface between discrete elements and finite elements using cohesive laws presented in the software Abacus. For model A and model B, the following slenderness levels are considered with the parameter B of the cross-section of the samples equal to 100 millimeters in all cases. And for the slenderness level equal to 2, a circular cross-section is also examined considering the boundary conditions applied in model A and model B, that is, using just discrete elements using a hybrid model. About the results, so the figure shows the axial compressive strength in the vertical axis and the slenderness levels analyzed in the horizontal axis for model A and the model B, with black and red colors respectively. So about the results, we can observe that model A and the model B have similar trends. For the frictionless boundary condition, this slenderness does not influence the results, as it's possible to see here with the solid red and the black lines. However, for the fixed boundary condition, this slenderness has a significant influence, and we can observe here in the dashed the black and the red lines, the maximum difference obtained is equal to about 250% for both models when we use the fixed boundary conditions and the different levels of slenderness. When we analyze here the influence of the cross-section shape, here the figure we have the axial compressive strength in the vertical axis, and in the horizontal axis we have the different models, model A and the model B, and also the different cross-section shapes. So about the figure, it's possible to observe the cross-section shape influence the compressive strength independently of the model applied, that is model A on the model B. And for the frictionless boundary condition, the average distance, the average difference between the models is equal to about 260%, whereas for the fixed boundary condition, such a value is equal to about 265%. So about these results, we also analyzed the rupture configuration. Here, just the model A and the model B, just for the frictionless boundary condition is shown, and also experimental evidence obtained from Bandeira, where the authors use Teflon to decrease the friction between the samples and the testing machine. As we can comparing the rupture configuration, it's possible to see a kind of agreement between the numerical results and the experimental ones. So concluding, from the results presented, it's possible to conclude that the contact boundary condition and specimen slenderness influence the compressive strength. The cross-section shape also influences the compressive strength, and the discrete element approach can be a good tool to analyze the damage in the final rupture configuration. In the future works, we expect to apply also the extended finite element to compare the results with those here presented and also with our experimental campaign. Thank you.